Bismillahirrahmanirrahim. Hello everyone, I hope you are all doing well. I welcome you all to the class of real analysis. Today lecture is very important lecture. In today lecture, we will discuss about the completeness of Q. I will share four methods to prove Q is not a complete ordered field. So, firstly, what strategy can be used to prove whether a given field is an ordered field or not, complete ordered field or not? We will choose any subset of a given field. We will choose any subset of a given field that is bounded above, that has an upper bound. But the supremum of that subset, it does not exist in that field F. Then that ordered field is not a complete ordered field. I again repeat, suppose I have to prove F is a complete ordered field. I will choose a subset A of F. A should be bounded above. A should be bounded above. Bounded above mean upper bound of A exists. Then F will not be complete ordered field if supremum of A exists but does not belong to F. Then F is called not a complete ordered field. If supremum of A exists in field F, then F is called complete ordered field. So I have to show Q is not complete ordered field. For this, I will show that I will choose any subset of Q. I will find the supremum of A, and at the last, I will show that supremum of A does not belong to Q, and that shows that Q is not complete ordered field. So this is our strategy that we can use to show that Q is not a complete ordered field. So in today's lecture, I will discuss three methods to prove Q is not complete ordered field. The fourth one I will discuss in the next lecture. Out of these four, two methods are already available in your textbook, Principle of Mathematical Analysis by Walter Rudin. And the third one that I like very much, and that is very interesting, that I will share after these two. In the last lecture, I have discussed about concept of largest element and the smallest element of a set. So I will recall the two subsets of rational number Q that I will use here to prove Q is not a complete ordered field. So the two subsets of Q that I will use here. The first one is A, that consists on all those positive rational numbers whose square is less than 2. And the second one is B, that consists on all those rational numbers whose square is greater than 2. If we write all the elements of this set A, if we write the elements of set A, this is the condition: x square is less than 2. X square less than 2 and x is positive. By taking square root on both sides, we have x is less than square root 2. It means your x lies between 0 to square root 2. In other words, your A is open interval 0 to square root 2. Now, what is the how we define the largest element? An element is called the largest element of a set A. Suppose this is our set A. If it is larger than every other element of set A, now the largest element of set A would be square root 2, that is greater than every other elements of set A. But this square root 2 does not belong to set A, so this set A has no largest element. That I have proved in our previous lectures. In the similar fashion, If we write elements of set B, then set B that consists on all those positive rational numbers whose square is greater than 2, x square is greater than 2. From this, by after taking square root, we have x greater than 2. Now this consists on all those rational numbers which are greater than square root 2. So these are square root 2 to positive infinity. So in the form of the interval, B consists on all those rationals that lies in the open interval square root 2 to infinity. So B consists on all those rational numbers that lies between these two, square root 2 to positive infinity. So this is our set A, that is an open interval 0 to under 2, and this is our set B. Now you can notice that as similar to set A, B has a no smallest element. The smallest element of a set is one of the element that is smaller than every other element of set B. So the smallest element of set B is square root 2. So the set B has a no smallest element. So now we will prove that Q is not complete ordered field. This is our basic discussion. Method 1. We have proved that if the set A, this is our set A, that might be invisible here, then A has a no largest element that I have discussed here. This set A has a no largest element or largest number in Q, and the set B has a no smallest number in Q. Now we show that Q is not complete ordered field. For this, it is sufficient to show that there exists a bounded above subset of Q that has no supremum in Q. I have already discussed that a field F is called not a complete. A field F will not a complete ordered field if it does not satisfy the completeness property, or in other words, it does not satisfy the supremum property, or also we can say that it does not satisfy the least upper bound property. So it is sufficient to show that there exists a bounded above subset of Q that has a no supremum in Q. So we show that this set A, that is this actually, has a no supremum in Q. We will select this set A. We will choose. We will start our theorem as suppose this is our set A, that is a subset of Q. Next we show that next we write as the set of all upper bounds of A. If you find the upper bounds of A is the open interval 0 to square root 2. So every number that is greater than 2 is the upper bound of A. So every number that is greater than under root 2 is actually the elements of B. So the elements of B are actually the upper bounds of A. I again repeat, upper bound of A are the elements that are greater than every element of A that consist on set B. So set B have all the elements that are the upper bounds of A. As the set of all upper bounds of A consist on all these elements, and let this set is equal to B. So we can notice that the supremum of A would be the smallest element of B if it exists. If I say what is the supremum of A, you will say that the supremum of A will be the square root 2 if it exists. Now this supremum of A, if it exists, this supremum is actually the smallest element of the set B. What is the smallest element of B? Smallest element of B is square root 2. That is actually the supremum of A. So the supremum of A would be the smallest element of B if it exists. But B has a no smallest element. We have proved it in our previous discussion. Hence, A has a no supremum because B has a no smallest element. That is actually the supremum of A, but B has a no smallest element. This implies that A has a no supremum in Q. In other words, Q has no least upper bound property. Hence, Q is not complete ordered field. Next, we move towards the second method. Okay, next we move towards the method number 2. At this time, I will suppose the set B as a subset of Q. The set B that has a no smallest element because B consists on all those rational numbers that lies between square root 2 to positive infinity. If we calculate what is the smallest element of the set B, it would be square root 2, but square root 2 is not a rational number, so square root 2 is not the smallest element of this set B. So the set B has a no smallest element. Now all the lower bounds of this set B, what are the lower bounds of set B? Set B consists on all those rational that start from square root 2 to infinity. Now all the numbers that are less than square root 2 will be lower bounds of set B. The numbers positive because in uh, both sets consist on positive rational numbers. So the numbers that are smaller than square root 2 consist on set A. So set A is working as here set of all lower bounds of B. Set A is actually the set of lower bounds of B, and set B is actually the set of upper bound of A. Now, what is the infimum of this set B? The infimum of set B would be square root 2, but that does not exist in set B. So to prove at this time Q is not a complete ordered field, I will use the property of infimum property. The infimum property says that any subset of any ordered field, any subset of any ordered field that has a lower bound has the infimum in that belong to that field. So if Q is not a complete ordered field, we will show that there exists a subset that is bounded below but has a no infimum in that set. So simply we will show that B has a no infimum in Q. B has a no infimum in Q. This is our target to show that. At this time we show that there exists a subset of Q that is bounded below but has no infimum in Q. So we show that the set B has no infimum in Q. As the set of lower bounds of B is lower bound of B consists on all the consist on set A, or in simply the lower bound of B is actually the set A. We can notice that infimum of B would be greatest element of A. The infimum of B that would be square root 2. This is actually the greatest element of A. Infimum of B would be greatest element of A. But we have proved that the set A has a no greatest element. This implies that infimum of B does not exist. But A has a no greatest element, hence B has a no infimum in Q. In other words, Q has a no greatest lower bound property, hence Q is not complete ordered field. So these are the two methods that are available in your textbook, Principle of Mathematical Analysis by Walter Rudin. Now I discuss the third approach that is very interesting to show that Q is not a complete ordered field. It is sufficient to show that there is a subset of Q which is bounded above but has a no supremum in Q. So I will find a subset of Q that is bounded above, but its supremum does not belong to Q. So let us suppose a subset S of Q that consists on actually the elements. Let this elements of set S are, the first element is 1, the second one is 1 plus 1 over 1 factorial, the third one is 1 plus 1 over 1 factorial plus 1 over 2 factorial, the fourth one is 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial. Similarly, other elements you can write. So clearly these R elements are actually rational numbers. So this set is a subset of Q. We can notice that every element of the set S is less than 3. The first element is 1, that is less than 3. The second element is 1 plus 1 over factorial, that is 2. The third one is 1 plus 1 over 1 factorial, this is 2. 1 over 2 factorial 0.5, this is 2.5. The third element is equal to 2.5. So every element you can calculate is less than 3. So S is bounded above. Mean to say every element is less than 3. So 3 is an upper bound of set S. So S is bounded above. But now we show that the supremum of S is bounded above because there exists an upper bound, that is 3. Every element of set S is less than 3, so 3 is an upper bound. This shows that S is bounded above. Next we show that the supremum of S does not exist in Q. To calculate supremum of S, we know that the Maclaurin series of exponential function e raised to power x is 1 plus x square over 2 factorial plus 1 over x cube over 3 factorial plus up to so on. If we put x is equal to 1 here, if we take x is equal to 1 here, this will become, the Maclaurin series will become e is equal to 1 plus 1 over factorial, 1 over 2 factorial, 1 over 3 factorial. Maclaurin series of e raised to power x is 1 plus x square by 2 factorial, x cube over 3 factorial up to so on. By replacing x is equal to 1 here, 1 plus 1, here you can write as x over 1 factorial. 1 over 1 factorial, 1 square, that is 1 over 2 factorial, 1 over 3 factorial. So on the right hand side, on the left hand side, if we put x is equal to 1, this will give us e. So this is Euler number, and the Euler number always lies between 2 and 3. So this also shows that our set S is bounded above by 3. This implies E lies between 2 and 3. Now, what is the supremum of this set? Here supremum of S is E. If you calculate the last number of this set S, what type of the number that belong to set S? The numbers that belong to set S are of the type this: 1 plus 1 over 1 factorial, 1 over 2 factorial, 1 over 3 factorial, 1 over 4 factorial. This is its fifth number. If we calculate its 100th number, this will become 99 factorial. If we calculate its nth number, this will become up to so on n minus 1 factorial. So when n approaches to infinity, mean to say the last number or infinite number, that number will be 1 plus 1 over 1 factorial, 1 over 2 factorial up to so on, which is actually simply equal to E. So the supremum of this set E is equal to E, but E is not a rational number. E is an irrational number. Hence the supremum of set S Supremum of S is equal to E. E is an irrational number that does not belong to Q. So S has no rational supremum in Q. Hence Q is not complete ordered field. So in today's lecture we have discussed three different methods to prove Q is not a complete ordered field. Inshallah, in the next lecture I will discuss another method that also shows Q is not a complete ordered field. I hope today's lecture is very helpful for you, and now you have a clear understanding about all of the discussion. Okay, take care. Allah Hafiz.